Sam, Shen, and I have focused on a problem we think is important. Many atmospheric and oceanic science professors say the biggest challenge facing their undergraduate students is poor preparation in mathematics. The students lack the mathematical knowledge and the skills needed for the courses in their major. And we think many of those students will face similar problems after they graduate and then either go on to grad school or else enter the job market. We think that they will find, many of them, that they still need to know more in math, statistics, and programming. And we look forward to discussing these issues with you today. That's why we're here. Now, we're not here to tell anybody what to do. And we realize that math departments in many universities often depend on the service courses they teach to students like your students majoring in various science fields. These courses also provide TA support for many grad students, and they help justify faculty positions for many mathematicians. And we also know that change is often difficult. We do not advocate throwing out the traditional math curriculum. We prefer making gradual changes. And to raise these issues and to propose some solutions, we wrote Climate Mathematics. The entire book can be taught in 3 semesters. It can replace all the usual required math courses that are outsourced to other departments to teach. It can also be used as supplemental reading or for self-study or as a useful reference and a toolkit. We're not here to sell books, but it's a very versatile book. In 2019, Sam was at NCAR for a UCAR members meeting, and something interesting happened. In a large breakout session, a poll was taken, and everybody in the room was asked to write down the single greatest challenge faced by students entering a meteorology program. There was no prior discussion. This wasn't multiple choice. Everybody chose their own words. Every person picked a single greatest challenge, one person, one vote. And in this list here are the 7 challenges that got the most votes. If you add up all the numbers, there's something like 62 people voted for these challenges. And except for a few votes for poor study skills, everybody in each of these challenges, everybody voted for math or programming or math plus physics. So there was overwhelming agreement of the people in that room that mathematical subjects were the single greatest challenge facing undergrad students entering programs in atmospheric science or closely related fields. Personally, I'd like to see more polls like this. You might decide to take a poll in your own department. Now, it's easy online to find the outsourced math courses that undergrad students in atmospheric and oceanic science take. It varies between universities, of course, but this list is representative. Here, the teaching is usually done by mathematics, statistics, and computer science instructors. The typical courses are calculus, several semesters, linear algebra, differential equations, introductory computing or programming, and probability and statistics. We coined the acronym RUM, R-U-M, to describe what we think math education for our students should be. R for relevant to the major courses. U for useful to the problems these students will face later in their research or in their jobs. And M for modern, meaning taking advantage of recent progress in areas such as computing power, big data, and user-friendly programming languages. The traditional approach fails to meet these criteria. It is too slow. For one thing, too slow. The undergrad students are still taking math courses in their 3rd year, and the math courses they take are often not well connected to each other or to the students' major courses. The students often realize that they're working hard on some math that they will never use, while they're not being taught some math that they will need. Their major professors often think these students have weak mathematics backgrounds. So the question we're posing is, how can we solve this problem? We think that solving it will take time and the ideas of many people, including many of you. The book we wrote is our modest contribution to this effort. We agree with this statement at the top of the slide here. Change is easy, improvement is far more difficult. Professor Porsche was the automotive engineer who founded the company that makes Porsche cars. Change is easy, improvement is far more difficult. Once again, we advocate gradual change, not revolutionary change. We're not throwing out the typical curriculum, but we do advocate taking up useful topics early and, yes, less useful topics later. We certainly insist on mathematical rigor. The portrait here is Gauss, and I put the Gauss picture on the slide to remind me to tell you that our book is definitely a mathematics book. We have a deep respect for many fundamental theoretical topics in mathematics. We use all the ones listed here, including Stokes' theorem, the divergence theorem, the fundamental theorem of calculus, Green's theorem, the mean value theorem, Taylor's theorem, and many, many others. We knew our book would be limited to some 400 pages, and we wanted teaching all of it in 3 semesters to be possible. So we were ruthless in leaving out many traditional topics that we felt were simply not useful, either in the courses that atmospheric and oceanic science undergrads would take, or in the jobs they would fill after graduating, or in grad school if they took that path. So by omitting these less useful topics, and by leaving many of them for elective courses later on, for example, we made space to introduce many new topics that matched our RUM criteria: relevant, useful, and modern. We include many useful computer codes. For those of you who've seen the book, there's a lot of codes in it, and the codes are in 2 powerful and popular languages. R is the language in the book, and Python is the language for equivalent codes that are available online. We also gave detailed treatments of empirical orthogonal functions and singular value decomposition. We devoted a lot of space and many codes to data analysis and visualization. And the person pictured here is Edward Lorenz of MIT, a scientific giant who contributed importantly to both mathematics and theoretical meteorology, including chaos theory and the concept of sensitive dependence on initial conditions, or the butterfly effect. Ed Lorenz, it's interesting to note, also coined the term empirical orthogonal functions. The Confucius quote at the top here is the epigraph of the book. I hear and I forget, I see and I remember, I do and I understand. We are convinced that students should understand mathematics by doing mathematics. Every important math topic in the book is taught using examples from atmospheric and oceanic and climate science applications. The 2 computer languages we use, R and Python, are both free, they're both open source, and they're both easy to learn. And the color map on the book cover is precipitation climatology over 38 years from 1979 to 2016. And one of the things we teach the students is how to make that figure. Here's the figure from inside the book. The data come from GPCP, the Global Precipitation Climatology Project. And in the book, we show how to find the data set online, how to download the data, how to analyze the data, how to create this publication quality graphic. All the data sets in the book are also available online on the book's website. We have a big emphasis on data handling and on data visualization. The list on the left on this slide is abbreviated chapter titles for the 11 main chapters in the book. So you get a good sense of the subjects we cover. We don't have any prerequisites here for anyone who's had high school mathematics knows what they need to know to start this book. There's dimensional analysis, there's programming, statistics, matrices, linear algebra, energy balance models, calculus, derivatives and integrals, conservation laws, computational graphics, empirical orthogonal functions, trends, global data, and the analysis of incomplete data. And as an example of how we approach important topics and how we create examples to instruct the students, I'll show you something from chapter 5 on this list, which is on energy balance models. This is a famous figure by Kevin Trenberth and John Fasulo of NCAR. It's in the book. It's the global energy flows with fairly recent data. Of course, the Earth today is not in a global energy balance. It's actually gaining about 1 watt per square meter. So climate is not in a steady state. It's warming, and because of human activities like burning fossil fuels. We start with this figure, and then we go and discuss a simple, the simplest perhaps, climate model, a zero-dimensional energy balance model. So the planet on the right-hand side in this figure is just a rotating spherical rock. It receives a constant solar irradiance intercepted by a disk facing the sun. The disk of the same radius is 4 times less area of the sphere. So the sphere rotates and receives an amount of energy per unit area that's 4 times smaller than the amount the disk with the same radius receives. And there's an energy balance that resulting if the sphere emits as much radiative energy as it absorbs. And so on that assumption, we can make an equation with no time derivatives. This is a steady state, simple energy balance model. Solar radiation absorbed on the left is equal to energy emitted on the right. And the right-hand side is assumes the black body assumption. So sigma is the Stefan Boltzmann constant, and the left-hand side is the absorbed energy, where alpha is the albedo of the planet, which for Earth is about 0.3. And S0 is the solar constant. So you solve this equation for T, the temperature, and it comes out to be minus 18 degrees Celsius, which is very wrong. It's about 33 degrees colder than the actual average surface temperature observed on the Earth. So why is the answer so wrong? Because the model is much too simple. It doesn't have any water, doesn't have an ocean, and doesn't have an atmosphere, and it doesn't have a greenhouse effect. And then we had a bright idea. We knew that the moon also has almost no water and has no ocean, no atmosphere, no greenhouse effect. And so we had fun developing an original energy balance model for the moon. It's not for the lunar average. Our model produces lunar surface temperature as a function of location on the moon. And we're lucky because there's a satellite that's been in orbit since 2009. And the satellite carries a radiometer named Diviner, and Diviner measures the lunar surface temperature. It's still functioning. And this picture here is Diviner data, shows temperature as a function of lunar latitude, the vertical coordinate, and longitude. And this temperature, these are observations now, varies from about 389 from the center of the figure on the right, that's the subsolar point, the hottest place on the moon's equator, to about 101 Kelvin on the side of the moon away from the sun, which is the left side of this figure. Now, I'm not going to show it, but our simple energy balance model produces a temperature map that looks just like this observed data map. The model's maximum temperature is 384 instead of the observation of 389 Kelvin. Its minimum is 100 Kelvin. What can be illustrating what can be done with the material in climate mathematics.